Okay, before the break, we stopped at these two graphs. So as you can see, a pure metal, or for example, copper, there's a change of properties if you add in 30% of zinc. So this is just an illustration. Look at the tensile strength of pure copper. At 30%, if you extend the cold work up, move to the left, you get about, this one is KSI imperial, but if you convert into Pascal, it will be 300 something, right? Don't worry, in your assessment, you will be seeing a unit SI graph. Well, you'll be seeing maybe another axis here. So same with this one. If you do 30% cold work also, you look at the yield strength. The yield strength will be 500 megapascal, right? So before the break, I explained to you on the whiteboard that same happened to the elongation also, right? Yeah. So let's look at how we apply the same graph, the same graph. So you compute, the tutorial question asks you, compute means to determine or to calculate the tensile strength or ductility and ductility percentage of elongation of cylindrical. This here, it gives you cylindrical, means there's a round shape, copper rod. If it's cold work, we tell you cold work means, you give you a hint already. You need to use the percentage of cold work equation. Such a diameter is reduced from original 15.2 to the last diameter, 12.2. How do you calculate the tensile strength? First, you calculate the percentage of cold work first. You take the original area. You take the big number minus the small number divided by original area, times 100%. So what is the answer from your calculator? 19. Okay, 90%. So you do. There's a square there. So yeah, so it's a calculation error, not 19, but it's 35.6%. No. Normally, this kind of question is a 3-mark question. You will be in the section A or section B question, right? So if the first question wrong already, then the rest also wrong. Any question? Yeah. Huh? Pi r square. No. They give you what? This is diameter. Clear up. Or you jam already. Yeah. The question give you diameter. D1 is 15.2. It becomes smaller. D2, 12.2 mm. What is the area? Yeah. It's a pi r square. But what is r? When you square, what do you get? Pi d square divided by 4. Or straight away you use pi r square. How to calculate the r? Diameter divided by 2. So pi r square. Okay, so I think the careless mistake here is a calculation. Don't make this a simple error. You are now in the degree level. Certificate level, if you're still asking what is a pi r square, still okay. But you're in the degree, it should be better. So you get the 35%, then you go to the back of the question. Normally all this graph will be at the back of the question. You go to the back of question, you flip the graph. Then you find the graph will say co-work on what material. Go and find the correct graph. Huh? So here it straight away give you the copper co-work graph. So percent of co-work 0 to 70%. Some graph give you until 100%, but we won't do until 100%. Right? So versus yield strength, this one is megapascal. So you use the left hand side graph versus x-axis. You already have 35.6%. So it's about here lah. You go to co-work here, 35, almost half lah, almost between 30 to 40. You choose the one. Again, in assessment, sometimes what we do is that we adjust the axis. Same with your ruler, standard ruler length. So you can like scale the number here. Okay. So when you solve a question with the graph, use your ruler to measure first. Measure, is it the same, or I can scale or not? If cannot scale, then you just agak-agak lah. Okay. There is a plus minus percentage in my answer script there, right? So here you go 35, and another one is this is the tensile strength. This is yield strength. All right. So there's one more. Huh? So these are the three graphs that we see just now. One is yield strength, one is tensile strength, one is the ductility. So don't use the wrong graph. Huh? So first, you go to the 35% around there. You move up, and we are dealing with copper. So you look at the copper line. Don't look the wrong one. Huh? You have three material here. Right? And of course, when it comes to test, you have more lines there. The purpose is to confuse you. So don't confuse by the line. So go to the co-work, go to the left, you get about, then all graph you do co-work first. 35%, move to the left, 35%. Yeah. So here, first graph is about 350 megapascal. Because the question asks you tensile strength, you go to the tensile strength graph on the middle, you read the reading, about 350 megapascal. On the slide here, I give you the textbook answer. But if your answer is 350, I still give you correct. It's roughly near, but if your answer is more than 400, means wrong already, something wrong. Okay. Then from here also, you go to 35%, move up, read the copper. Copper is a red line. It's a red line. So you move to the left is about 6 or 7%. Sometimes you can, if you give 8%, I still give you correct. 9% is wrong already, because 9% a bit too high. Okay. So you have two answers here, then you solve the problem. This is just an introduction. Right? Of course, your test or your final exam won't be this easy. Okay. Any question on finding the strength and the elongation? Okay. So from example 1, you try to think the question, how you reverse the question. Sometimes this is question, it gives you the final spec or product spec, then you find the co-work, from co-work to final spec. So the question can be re-engineered to move backward. We're given a certain tensile strength, you need to find how many percent co-work that you need. Okay. This normally, if you reverse that, normally will happen in the industry, because the spec is the design problem. Right? If you want to design a vessel or boat body, for example, or the truss body, then you already have the maximum load that you can use. Right? So you have a tensile and the elongation maximum that you can play with. So you need to design how many co-work that you need to do. There's a process. There's a process of strengthening, or in co-work, there are three processes: recovery, recrystallization, and grain growth. There are three processes. There are three processes. So as you can see on the graph here, how you read the graph. Here you have this diagram. You start with the diagram on the bottom here. You start with the x-axis. X-axis is temperature. And then there are three regions. First, recovery. There's a temperature below recrystallization. We call it recovery stage. The important parameter on this graph is recrystallization temperature. Below this line on the left is recovery. So the maximum point of recrystallization, it fall into it passed the recrystallization already, right? So there will be a start to have a grain, more grain happen. Okay. So recrystallization is a new grain start to happen. Means a new, right? And you can see the strain and internal residual stress. So you look at the middle graph here. Below the recrystallization, there are three lines here. The blue line is ductility. You know, ductility, it deals with percentage of co-work or percentage of elongation, right? So below recrystallization, you see there is a small increase of the percentage of elongation that you can get. But when it reaches recrystallization, means there's more grain inside the structure. Then you see the ductility will increase and it continue to fade out. Same with the strain. The strain, the dot line here, is flat. Once the recrystallization start, the value of strain will drop. Because why? Because grain is like a defect. It's like you can see it as there's a hole there. Like new, it's like a chicken pox. The new chicken pox inside the grain, the metal there. So you have more chicken pox means more defect, more holes there. So when more hole, the strain will drop. Okay. And then the more temperature you give, like the size of chicken pox become bigger. Okay. Hardness also drop. Hardness flat, and then recrystallization, hardness also drop. Why hardness drop is like, imagine chicken pox. The more holes you have, the more easier it deform. Like when you press, it's more easier to press. So hardness drop. Okay. So the phrase will be recovery, recrystallization, and grain growth. There are three important phrases when we talk about deformation of metals. Before all in other module, especially you learn about finite element analysis or calculate the structures. It will happen either on the left-hand side or right-hand side. You have a value that maybe in the co-work percentage, which is very strong behavior. So normally you do use for calculation, it will be on the left-hand side of the graph. You're still in the recovery stage. Okay, the rest you read. One technical word called annealing. Annealing is involved with temperature. You reheat the metals. It's called annealing. Annealing is linked with the temperature. Okay, means the raw material from the factory, from the furnace, it come out. Then if you reheat again, the process is called annealing. Right? You heat one more time, also it's also called annealing. Right? Then in some textbook, they will mention degree of softening. Degree of softening, there are two: partial annul or full annul. Right? Partial annul means you heat until a certain temperature, then you cool it back. Full annealing means you ramp the temperature up until a maximum, then you cool it down. Okay. And you know, the higher temperature, the metal will become softer. Right? Okay. Next, we look at the structure of heavily cold metal before reheating. This is called before annealing. Before annealing. So on the diagram here, you see there's a change of the structure. Before the roller, you see there's a grain very big, but when it's squeezed, the process come up, the grain become very long and thin. So here, when during the cold work, strain energy was expended in plastic deformation stored in the metals in the form of dislocation and other imperfection, such as point defect. There are lots of defect there previously, right? So you talk about strain energy, strain energy expanded. So if you squeeze or you roll it, the output will have a higher internal energy because it's squeezed in a pack it, so there's lots of internal energy. So this is a sample under microscope, 100% power, 100 times. You can see that this is cold work with 85% reduction. You see the grain is very flat. Okay. This is 100%. If you increase up to 20,000%, means you look into one of the spot here, you will see the structure will look like this. All right. Okay. Next, we look at recovery. When the metal was cold work, just below the recrystallization temperature range, internal stress in the metal are released. So if it heat up, then before it reach recrystallization temperature, it cool down. It will, the internal stress of the metal is relieved, means it go back recovery, means no energy, no stress inside the metals. Okay. If it go to recrystallization, means you'll see new grains or new chicken pox already, means there's a stress. There's a stress happen inside the structure already. Okay. So you can see on the top graph here, we look at the top graph, internal residue will decrease. Will decrease. Imagine the metals, if you heat up, means the metal will, when it heat, it will expand. It give you more space for the metals atom to move. Right? So no rest stress. Okay. The rest you read. Recovery. So during the recovery stage, what is important here is that it allowed dislocation or defect to rearrange. Means if you heat up the dislocation, the defect will find place, the surrounding atom will find place to slot in the empty space. Right? Okay. This is just for your information. The diagram on the center here is just for your information. So let's say on the diagram, this small little line here is the dislocation. Then after reheating the metals, the dislocation will find space to rearrange. It become more tidy lah. Okay, the rest you read, huh? Recovery. One point to take home is that the strain is reduced a little bit. When you heat up, the strain will reduce a bit, not more. Huh? Okay, then the recrystallization is important. So what happened to the recrystallization is that new strain-free grains will appear or nucleate in the recovered metal structure. Pay attention to the way when you explain about recrystallization, you need to mention recovered metal structure. This RECOVERD, recovered, you need to mention recovered. Why? Because recrystallization is past the recovery phase. So you need to use recovered, the keyword, recovered metal structure when you explain recrystallization. Or you can explain in a way that the phrase must after the recovery, must pass the recovery phase. All right. So you will see this one on the middle here. This one is in the recovery phase just now. But when you roll, then you get a very straight line structure. But when it become recrystallization, it's like a chicken pox. You have a chicken pox on the structure. So you see there's a hole there. Okay. So when you go into lab later, when you look at the sample, you need to explain whether this metal have recrystallization or what kind of process that might be happen on the crystal structure. You will see something like this, right? Okay, the rest you read. This is the textbook definition for recrystallization. Recrystallization textbook give you that a new set of strain-free and equal axial grain, or in a more simplified word, a new set of grain was developed that have a low dislocation density and are characteristic of a pre-coat work condition. Okay. Important word for recrystallization is new grain. New grains was happen. So this is a diagram, a very important diagram. Normally appeared in the question section A, ask you to explain plastic deform process, plastically deformed process under co-work and involved with recrystallization process. Then you can see it start from the middle one, recrystallization. Then you have more grain here. Okay, more grain. Okay. Okay, then if it's long enough, the time is long enough, at the temperature with recrystallization take place. So when you increase the temperature up to a certain time, when the co-work is completely replaced with recrystallized grain structure, means the recrystallization completed, the process is completed. in the industry, how you know that recrystallization is already complete? You will see this kind of distribution maintained at a certain time. After recrystallization, you see on the left-hand side diagram, it will become bigger and bigger. This one, this size, this white space here will become bigger and bigger. Okay. Okay. Primary recrystallization, you have two mechanisms, means there are two ways of happening to make this recrystallization process. First, isolated nucleus, they expand from a deformed grain, or original high angle grain boundaries, they can move, migrate into a more highly deformed region of the metals. So A is isolated nucleus. So you have a nucleus of recrystallized grain. So it will from the grain itself, it will grow from the grain itself, means more grain from the grain itself, isolated nucleus. Another one is, let's say this is there's a hole there, then it will stretch, this one, it will grow into the region. So you imagine as a chicken pox lah. So how recrystallization or primary recrystallization happen? Or you see the word explain using explain the mechanism of primary recrystallization. What we expect is we expect you to draw these two diagrams and then explain. One is chicken pox, you grow on the chicken pox itself, you expand. Another one is you find a space and then it grow from the space there. Okay. Another one is from the same graph, tensile strength drop, what we explained just now, tensile strength drop during the recrystallization process. Ductility increase by annealing treatment, means you increase the temperature that cause the metal structure to be recrystallized. Okay, so it's a good practice to draw this diagram. Important is this one and this one. You draw this diagram into three reasons. Temperature below recrystallization temperature is called recovery. Then recrystallization process, and then continue. Continue. Then there are two more graphs here. On the left here, this is copper zinc, 85 copper, 15% zinc. Effect of annealing temperature on the tensile strength on the left. Left is tensile strength, right is a percentage of elongation of 50% cold work. Okay. This is annealing time at 1 hour. At 1 hour, so you can see the temperature. As you increase the temperature, the tensile strength drop. Tensile strength drop. Okay. What I mean by tensile strength? Again, on the tensile graph, stress strain, you have a graph there. Maximum point is your tensile strength, or UTS. Maximum point, and 2% or at the end of the elastic is called yield strength. Yield strength, either you can simplify by finding the last end. If the question asks you to do 2%, then this one also can find yield strength. There are two way lah, but there's an error between the first yield number and second yield number. Okay, because nobody know where is the plastic elastic exactly happen unless you observe under microscope. Okay, so there are two ways lah. One, you want to fast one, you go to the last point of the elastic line, then you can take as a U. Or more standard way is that you find 2% according to American standard. 2% of the strain, or 0.002, you draw a line, then that is your U point. Elongation, also you can see the graph, elongation increase at a certain temperature. Okay. So these are the example of a point of interest. Okay. This is another textbook graph that is more clearer than the picture just now. So as you can see, the graph x-axis always temperature, or call it annealing temperature. We heat it up. Then there's a grain size here. The grain size only appeared when there's a recrystallization process. So grain size will happen in the recrystallization and increase the grain size. Right, the green line at the bottom here. Right. So you can see before the recrystallization, there is a recovery here. Recovery grains here. Then recrystallization, you have a mixture of hole here, right? Or new grain. We call it new grain. Or you can illustrate as a chicken pox. But in your answer, don't write chicken pox. Don't write chicken pox. Just write new grain appeared in the structure. Then, as more and more new grain develop, then it become bigger and bigger grain. Bigger and bigger grain. Then there is a two line here. One is the tensile strength, one is ductility. So again, you see the recrystallization will change the mechanical properties of the metals. All right. So on this graph also very important. As you can see, where does the recrystallization happen? So you have recrystallization temperature and melting temperature. Let's take a normal material, aluminium. Aluminium recrystallization is 80%, 80 degree, but the melting temperature is 660. Okay. So where does this 80 happen? If you look at the graph here, 80, this is not, you cannot roughly this is for blast alloy. This is for pure metals, right? Important is the recrystallization temperature. But the behavior of the graph will almost same. This graph, this diagram is very important. You should able to draw what is recovery stage, what is the recrystallization stage diagram, and the grain growth diagram. Recovery, recrystallization, and grain growth. These are the three processes that you should able to draw or illustrate with diagram. Okay. Okay. So this is the industry process of continuous heating or annealing schematic diagram. As you can see, the products was from the left to right. So you will go here, go up and down, and then inside here there's a heating temperature, right, and come out. Okay, let's watch this video. It's a big machine, but the important process here is heating up the metals. So the motor go in, annealing temperature start from this point until the end point. So recrystallization start to happen inside the metals. So this is commercial information. Okay. Now, once you understand the recrystallization process, important is these three lines: the strain, ductility, and hardness. Right. So it depends on the process, the end process that you want. You can control the strain. If you don't want the, if you want to reduce the, increase the ductility, then you do recrystallization. Right? You want to reduce the hardness, you also do this recrystallization. You want to reduce the strain, also recrystallization. Right? There are a few factors. I'll give you all the answer. Important factor that affect this region here, recrystallization, is the amount of prior deformation of the metal. So before you go inside the machine, you need to check what is the amount of deformation already inside the metals. Second, the temperature, time, initial grain size, and composition of the metal and alloy. So these are the 5 factors that affect the recrystallization. So if the question asks about recrystallization, what is expected is this diagram. You draw this diagram, draw the recovery, recrystallization, and grain growth, right? Or you use this diagram. Use this diagram, right? Draw this diagram and then highlight the region, recrystallization, grain growth, right? Then your x-axis, you don't need to put in all this number. You just need to tell what is x. X is your annealing temperature. Then the behavior inside the metals, what happened, right? Okay, then what affect this recrystallization? There are 5. No, normally you don't need to give 5. You only need to mention 3 of this one. Okay. Okay. Then the rest you read lah. This is how the recrystallization happen. Okay. This one you read. This one is when you work in the metal company, then you will see this graph. What happened between the recrystallization and completed? Uh, the axis is time versus 1000 over T in Kelvin. This one, this type of data in material science, you will see this word called Arrhenius. Arrhenius is very famous for material, especially recrystallization process. Okay, the rest you read. Okay. Okay, let's look at example 2. Then we call it a day. So example 2, I should hide all this, but never mind. If it takes 9 10 power 3 minutes to recrystallize a piece of copper at 88 degrees C and 200 minutes at 135 Celsius, what is the activation energy for the process, assuming the process obey Arrhenius rate equation? And the time to recrystalline. equal to CEQ divided by RT, where R equal to 8 point something, T is in Kelvin. Right? How do we solve this one? So you need to convert your time into second, right? In this case, normally I'll convert into second, but temperature convert to Kelvin. So you have two time and temperature. Okay, so this is the equation given in the question. T equal to CEQ divided by RT. You put in the time 9.0 times 10 power 3 minute divided equal to CEQ divided by RT. You change the T into Kelvin. You do the same for the second case, which is 200 minute. So the T you put into 200 minute. Then you change the temperature into Kelvin. 135 Celsius equal to 408 Kelvin. You have two equation 1 and equation 2. So you can remove the constant value by dividing two equations. You take 1 divided by 2, you cancel the C. Then you have the epsilon equation, E power something. So epsilon you log two sides, then you solve logarithm equation. Okay, so when you divide, you get 45 equal to exponential E. First one minus this one, you know that you divide something, the exponential is first one minus second one, right? So the R is given, R is 8 point something. Then you can find your Q. There's only missing is your Q. Q is your activation energy. So from the middle equation, you have exponential, so you log not log, ln E equal 1. Huh? So ln 45 and then the exponential, then you solve, you get your Q equal to almost 100 kilojoule per mole. Okay, so this is Arrhenius equation. Huh? T equal to CEQ divided by RT. Also very straightforward, this kind of question, very straightforward. Any question for this one? No, Let me see, example 3. Okay, let's go one more, or no? Okay, example 3 is the co-work example, that how you apply. So you have a rod, non-co-work brass have initial diameters. You are given initial diameter 6, and when you see non-co-work, the question actually asks you the co-work equation. When you see co-work, non-co-work or co-work, actually answer want you to use this equation. Percentage of co-work equal to original area minus deformed area divided by original area times 100%. So given initial diameter to be co-work by drawing, this one drawing, cross-section area reduced. It requires to have co-work yield strength at least 345 megapascal and a ductility in excess of 20%, means ductility must more than 20%. In addition, a final diameter, the final diameter was given. So actually the final diameter was given, so the A deformation was given, initial was given, so you're able to find the co-work. Okay, so how to describe the manner which this procedure may be carried out? So you need to describe the process, how the process need to be carried out. This example 3 is a final exam standard question. So it's an application of a graph that you see since the beginning of this chapter. Then you need to do some calculation and then explain the process. So you consider the process, right? So you calculate the percentage first. So you can calculate, right? Original is 6.4 mm diameter. Deform up to a final diameter is 5. 6.4 to 5.1. Right? Remember to square your answer because it's a pi r square equation. Remember to square. Huh? So you get percentage of co-work here is 36.5%. Make sense? The percentage of co-work in this case is 35%. So you know that the whole process involved 35% co-work. Then you go to the graph. You have 3 graphs just now. Then you look at the customer requirement. You have this answer, 36.5%. You go to the graph there, you draw 36.5%. You use your ruler, draw straight line up for 3 graphs. You draw. Then you get answer for yield strength. You get answer for yield strength is 400 something. 400 something. So in the exam, if this kind of graph give you the answer, I can accept up to 430 maximum. Okay, more than 430 means you don't know how to read graph already. Right? So you get strength 410 Pascal. For tensile strength is 500 roughly. Ductility is about 8% if you do co-work, 36.5%. Then it will tell you that you need to have co-work yield strength at least 345 Pascal. Here, your yield strength on the graph here, it already passed the customer requirement. Because now, after you've done 36.5%, your yield strength already reached 400, but the customer only want 345. But you look at your ductility. Your ductility must more than 20%. Now, if you do 36.5%, you only get 8% elongation, which is not your customer want. So you as an engineer, how you make adjustment in your process? Huh? No. What are the things that you can adjust in your factory floor? If you have these 3 graphs, then you do calculation or you know how to calculate percentage, from original 6.4, you reduce it to 5.1, right? This is a very industrial problem. This is your raw material, 6.4. And then this is the end you want to send to your customer one. Diameter 5.1. Then you know that from here to here is 36.5 co-work. But if you do this process, your yield strength pass, but ductility fail. How do you meet this? How do you change the process so that you meet the customer requirement? Customer only look at this one. He doesn't care what happened before. So how do you do? Change the line. Okay.
Change diameter.
Huh?
Change diameter, right? I change a bit so.
Then this one, right? Huh? This one. This one cannot. Customer want this one. It's like you order to the factory. I want this one. Means you can only play with before. This is the first point you look at. Then, if you do previously 36.5, your stress pass, but your elongation percentage fail. How do you make this pass? How? Try to think. Okay, I try to think. Now your customer need this one. If you do this process, you get the tensile yield strength pass already, and more than what customer want. Now the ductility percentage fail. How you increase this one to customer want what? 20%. How? What can you play? And just now you see you can change this diameter. How? Yeah. Yes. Change the percentage of co-work. How? This one is too much, right? Too high, right? So you can reduce this one lower, right? Because this is the final diameter you cannot change already. And the stress here, the yield strength here, actually when you reduce, you're still meeting the customer requirement. You don't want to touch this one, you touch this one. So what you do? Customer want 20%, right? So you go here. Minimum you need this 20%. You move here and you are dealing with what? Brass. So 20% go here. Move down, how many percent? Later lah, later. So what you do is you go to what customer want first. What customer want? How many percent elongation? 20%. Go here, move down about 20 something lah, about 24 or 22, that one lah. Okay. So here, if you want to get 20%, the co-work percentage will be 22 to 24% on the graph. Then you go to here. You check the minimum value you get from here, 20, let's say 22. 22, you move up. You move to the left, you're about 350 about, right? So what customer want? 345, you still pass, no? You still pass. So this is how you readjust your factory floor process. What you do, you check the percentage co-work that pass the two parameter. You adjust until it pass the 2. Then you move backward. When you pass, okay, then you know from this case, I know 22% is I can do. But you can also check this one. 345 is about 345 here. You move here, move down. It's almost like 22. So you cannot go lower than 22. If you go lower, you cannot meet the 345. You check here also. If it 20%, if it's more than 20%, also cannot. Less also cannot. Less, that one fail. Right? So you fix at 20, 22, 23%. All right. So here, yield strength certified pass, but the ductility fail. So alternative, alternative, in this case, I go in 345. I can move from here or here, same. On the slide here, I move from the left. I move down about 22, 21%, because this graph is very small. The one that you get in your final exam will be very big graph. So you should able to get exact value. Then let's say I get 20%, I go here, 20%, I go up. 20% elongation, I move down. It's about 20 something. So I compare two graphs, will be 20 to 23% to meet the two criteria. Okay. So We take the average, which is maybe 21%, 22%. Then you do calculation, the cohort calculation, right? You have the n diameter, you cannot change already. So what you can change is the original one. So you have one unknown to solve here. You fit in this one, the AO you need to find. AO you find a diameter origin one. Okay? You find original diameter is 5.8. You see the question try to confuse you actually. So try to look deep into the question. This one actually 6.4 is actually a confusing factor. It try to confuse you, right? But you need to stay cool and try to look at what customer want. Then work back on the graph. Okay. Because the customer never know what size you use in your factory. He only cares what you can deliver to them. Okay. So your answer for this question is that you use 5.8 mm diameter material, then you follow by recrystallization treatment, which reach the 21% cowork, right? Then you will reach